Welcome back, my friends. So in our last explainer, we really got into the weeds with TCP. We figured out how to build this amazingly reliable pipe over the internet, which, as we know, is a complete mess. So our data's getting there, it's all in one piece, it's in the right order, and that's a huge win.
But here's the thing, and this is where it gets really serious. Just because that pipe is solid doesn't mean it's private. Not at all.
Is the data that's flowing through that pipe actually safe? I mean, can somebody just come along, tap into it, and start listening to our conversation? Without the right security, the answer to that is a big, scary yes.
And look, this isn't some academic exercise. This is a massive, real-world risk. Just picture it. All your perfectly ordered packets, your usernames, your passwords, your secret API keys, just flowing out there in the clear for literally anyone with a simple tool to see. That, my friends, is a nightmare scenario, and it's our job to prevent it.
So how do we fix this mess? Well, this is where TLS comes in, Transport Layer Security. This is the hero of our story today. You can think of it like this security protocol that we wrap right around our TCP pipe, giving it a complete shield of security. So what does this shield, this TLS thing, actually do for us? Well, it gives us three absolutely critical guarantees. I like to think of them as the three pillars of any secure connection: encryption, authentication, and integrity. We're going to break down every single one of them, so let's get right into it.
Okay, first up, encryption. This is probably the one you've heard of. It's basically the art of scrambling our data so it looks like complete gibberish to anyone who's not supposed to see it. So if a snooper taps the line, they don't see your password. They just see a jumbled mess of random characters. But wait a minute. This brings up a classic paradox, right? A real chicken and egg problem. To encrypt the conversation, both the client and the server need to have the same secret key. But how on earth do they share that key without just sending it in plain text? Because if they did that, the snooper would just grab the key and decrypt everything. And the solution to this is it's brilliant. TLS uses what's called a hybrid approach. It actually uses two different kinds of encryption. First, to get things started, it uses asymmetric encryption. Now, this one is kind of slow and takes a lot of CPU power. But here's the magic trick. It allows the client and server to agree on a shared secret without ever actually sending the secret itself over the network. Then, once they both have that secret, they switch, they move over to the super fast, super efficient, symmetric encryption for all the rest of the communication. It's really the best of both worlds.
Now, I know there's this old myth floating around that TLS is too slow, that the overhead is going to kill your performance. Look, maybe that was kind of true like 10 years ago, but not anymore. Modern CPUs have special instructions built right in to handle this stuff. So the real takeaway, the thing I want you to remember, is that you should be using TLS for everything. I'm serious. Even for traffic between your own microservices inside your own private network. There's just no excuse not to. Okay, so pillar one is handled. Our data is now gibberish to any outsiders. That's awesome. But this leads us straight to our second pillar, authentication. How do I, as a client, really know that I'm talking to Google's server and not some hacker's laptop in a coffee shop that's pretending to be Google? How do we prove who we're talking to?
The answer is digital certificates. And the best way to think about this is like an ID card. A server has to present its certificate, which is its official ID. Now, this ID card isn't something it can just make up. It has to be issued by a trusted third party, what we call a certificate authority, or a CA. Your computer, your browser, they all come with a list of these CAs that they trust by default. So when a server shows you its ID, your computer just checks the signature. Was it signed by one of the CAs on my trusted list? If the answer is yes, we're good to go. We trust the server. That whole system is what we call the chain of trust.
And this system, this chain of trust, is incredibly important because when you mismanage it, it leads to the single biggest cause of major outages for big applications.
That's right, expired certificates. It sounds so simple, right? So boring. But I promise you, this takes down huge services every single year.
Just think it through. If the server's ID card is expired, your browser or your client is going to look at it and say, nope, I don't trust this, and it will just refuse to connect. That's it. Game over. Your entire service is down. So please, please, please invest in automation to monitor and renew your certificates. Don't be that engineer who gets paged at 3 a.m. and takes down production because you forgot to renew a cert. All right, on to our third and final pillar, integrity. So we've encrypted our data so no one can read it, and we've authenticated the server so we know who we're talking to, but What if an attacker in the middle doesn't just read the data, but what if they actually change it while it's in flight? What if they could change a bank transfer for $10 into a transfer for $1,000?
This is what integrity is all about, and TLS prevents this using something called an HMAC. The easiest way to think about an HMAC is like a unique, tamper-proof fingerprint for every single message. The sender calculates this fingerprint using the secret key we already agreed on. Then, when the message gets to the receiver, it calculates the fingerprint all over again. If the two fingerprints match, we know the message is authentic and nobody has messed with it. If they don't match, we throw it away immediately. Now, some of you with a sharp eye might be thinking, hey, wait a minute, doesn't TCP already have a checksum for this kind of thing? And that's a great question. It does. But here's the deal. The TCP checksum is weak. It was designed back in the day to catch accidental errors, like bit flips from noisy network gear. It was never designed to stop a clever malicious attacker. The TLS HMAC, on the other hand, is cryptographically strong. It's built for security. At cloud scale, TCP's checksum just isn't good enough. So there we have it. Our three pillars: encryption, authentication, and integrity. But how do we actually get all of this set up? Well, it all happens at the very start of the connection in this carefully choreographed negotiation. A little dance, if you will, called the TLS handshake.
Back in the old days with TLS 1.2, this dance was a bit clunky. There was a lot of back and forth. It took 4 separate steps, which went 2 full round trips between the client and the server before you could send a single byte of actual data. And in the world of network performance, round trips are the absolute enemy. They add up to a lot of user-facing latency.
And this, my friends, is why TLS 1.3 is such a massive deal. The engineers completely streamlined this dance. The client is now way smarter. It basically sends everything the server might need right up front. It even takes a guess at the server's preferred settings. This lets the server finalize everything in one single response. They literally cut the handshake in half, from 2 round trips down to just 1. For performance, this is an absolute game changer.
So let's wrap this all up. The bottom line is this: security isn't totally free. It costs you a little bit of latency, that 1 round trip handshake, and it uses a tiny bit of CPU. But when you compare that tiny cost to the alternative, sending your users data in plain text for anyone to steal and modify, well, it's not even a question. It is non-negotiable. It's absolutely essential.
Okay, so we've done it. We have a solid, reliable, and now fully secure pipe between our client and our server. The data is safe. But this raises a whole new question, doesn't it? Before you can even do a TCP connection or a TLS handshake, how does your browser even know the IP address for google.com? How does it find the server in the first place? Well, that's what we're going to cover next time as we dive into the phone book of the internet itself, DNS. You are not going to want to miss it. I'll see you then.